How to set up a home laboratory, over 200 sample experiments. The Golden Chemistry book, Chemistry Experiments. How to set up a home laboratory, over 200 sample experiments, by Robert Brent, illustrated by Harry Lazarus. Words used by chemists. Acid, a hydrogen-containing compound that relates hydrogen ions in solution. Alloy, a material made up of combining two or more metals. Analysis, breaking down a compound into two or more substances. Anhydrous, free-form water. Atom, the smallest unit of an element that can enter into the making of chemical compounds. Atomic weight, the weight of an atom compared with the weight of an oxygen atom set at 16. Base, a compound containing the hydrogen group OH. Catalyst, substance that can help in chemical reaction without it. Chemical change of a substance into another substance having different properties. Chemistry, a branch of science dealing with composition or substance and the change that can be made in them. Combustion, burning, a chemical change that proceeds heat and light, produces heat and light. Compound, substance consisting of two or more different kinds of atoms. Definite properties by weight, indefinite properties by weight. Crystal, a solid in which atoms or molecules are arranged in a defined pattern. Density, the weight of a liquid in a solid or in grams per centimeter or millimeters. Distillate, a liquid that has been turned into vapor and again cooled with a liquid. Distillation, the process of producing a distillate. Ductile, capable of being drawn into a wire. Breaking down a substance by passing an electric current through it. Electrolyte, a substance that when in a solution or when melted will conduct an electric current. Mercury, lead, copper. Element, a substance that contains only one kind of atom. Equation, a complete description of a chemical reaction by the use of symbols, formulas, and signs. Evaporation, the changing of substance into vapor. Also, the process of removing water by heating. Filtrate, a liquid obtained by filtration. Filtration, the process of straining a liquid from a solid. Boris Vitriol, usually filter what paper. Formula, a group of symbols and numbers giving the composition of a compound. Hydrate, a compound containing loosely bound water, hydration, water, or crystallization that can be driven off by heating. Hydroxide, a compound that contains the hydroxyl OH radical. Ion, an electrically charged atom or group of atoms. Radical, malleable, capable of being armored or rolled into a thin sheet. Matter, anything that takes up space and has light. Metal, an element that is a good conductor of electricity and has luster, whose oxide forms a base with water. Metalloid, an element that has proper ties to both metals and non-metals. Mixture, mingling of substances that not combine chemically. Molecular weight, the sum of atomic weight of the atoms that make up molecule of a compound. The smallest unit of a compound occurs in the free state. Neutralization, the reaction of an acid base to give a salt in the water. Non-metal, an element that is a poor conductor of electricity. Does not have luster and whose oxide forms an acid when combined with water. Organic chemistry, the chemistry of the carbon compounds. Oxidation, the process by which a substance combined with oxygen precipitate an isolate form in a solution by chemical reaction. Radical, group of atoms that behave chemically as a single atom. Reaction, a chemical chain. Reduction, a removal of oxygen, the opposite of oxidation. Solid compound other than water formed by reaction of an acid and base. The base, saturated solution, the solution that contains the maximum amount of solute under the conditions. Solidity, the number of grams of a solute needed to make a saturated solution in 100 grams of solvent. Solute, a substance dissolved in a solvent. Solution, a non-setting mixture of solute is solvent. Solvent, a liquid in which solute dissolves. Sublimation, a process by which the solute is turned into vapor and again cooled into a solid without passing to a liquid stage. Subscript, a small numeral indicating the number of atoms of a certain element in the formula of compound substance and a specific kind of matter, whether element, compound, or mixture. Symbol, a letter or two letters appear. Two letters representing one atom of an element. Synthesis, the making up of a compound from simpler compounds or from elements, the opposite of analysis. Valence, the number of hydrogen atoms which one atom of an element can displace, in which it can unite. Contents. The importance of chemistry. Every home kitchen is a chemical laboratory. Cooking and cleaning are chemical process. There is hardly a boy or a girl alive who is not keenly interested in finding out about things, and that's exactly what chemistry is about. Finding out about things, finding out what things are made of, and what changes they undergo. What things, anything, everything. Take a look around you. All the things you see and lots of things you can't see have to do with the science of chemistry. Let's start with yourself. The air you breathe is a mixture of chemical substances, and processes of breathing is a chemical reaction. The food you eat are all chemical products, and the ways in which your body turns them into muscles and bone, nerves, and brain cells are some of the greatest of all chemical mysteries. The clothes you wear, the books you read, the medicine you take, the house in which you live All of these are products of chemistry. So is the family car. The metal in it, the rubber on which it rolls, the gas that moves it. Nature itself is a tremendous chemical laboratory. Everything in nature is forever passing through chemical changes. Here on Earth, plants and animals. Insect means healthier livestock. Chemistry provides fuel for all kinds of transportation, purification of water. Grow die, and decay. Rocks crack and crumble under the influence of air and water. In the universe, new stars are formed, others fade. The sun that gives us heat and light and energy is a flaming furnace of chemical processes that will eventually burn itself out billions of years from now. Chemistry is one of the most important of all science for human welfare. Chemistry means the difference between poverty and starvation and the abundant life. The proper use of chemistry makes it possible for farmers to feed the world's ever-increasing population, for engineers to develop new means of transportation and communication that will bring the peoples of the world closer together, for doctors to cure the diseases of mankind, for manufacturers to produce thousands of items that are necessary for better and richer living. And this is only the beginning. Within recent years, scientists have succeeded in penetrating into the innermost secret of chemical substances and have begun to make use of the tremendous force that lies hidden in them. This atomic power opens up amazing possibilities of the future. You will live in a world in which your chemistry will become ever more important to understand. That world, it is necessary to understand the truth and laws of which modern chemistry is based, and learn how chemists of the past unraveled them. This book will help you get this insight, not alone by your reading it, but also your conscientiously doing the experiments described and learning what each of them has to tell you. Paper and printers ink are made with help of chemistry. United States is the world's leading producer of steel. Atomic energy for the future. Oil is the basis of the countless chemical products. Symbols used by alchemists: sublimate, alum, vitriol, borax, copper. Chemists of the past many thousands of years ago, an early ancestor of yours pushed a stick into the hot lava flowing from an erupting volcano. The stick burst into fire. He held it up as a torch. It gave off light and heat. Finally turned into ashes. This ancient man might be considered the world's first chemist. He had actually taken a substance called wood and had, by a chemical process called combustion or burning, turned it into something else. The discovery of the use of fire was the first great step leading towards modern chemistry. Fire made it possible to turn raw foodstuffs into edible meals, to bake, shape clay into pottery, to make glass, to drive metal out of their ores. For thousands of years, people were chiefly interested in the result of what they did. They didn't care about what happened or why it happened. It was only about 2,500 years ago that philosophers began to wonder about what things are made of and what happened when things change into something else. Around 4000 BC, in Greece, a thinker by the name of Empedocles came up with an idea that seemed to make sense. He explained that everything in the world was made up from just four things, which he called elements: fire, water, air, and earth. Think of the burning stick mentioned above. It gave off fire, so obviously the stick had to contain fire. It sizzled, which meant there was water in it. It smoked, and smoke would be some kind of air. It left ashes, and ashes are earth. As certainly everyone should know, everyone except another Greek, Democritus, born around the time when Empedocles died, he had a different notion, that all matter was made up of tiny particles he called atoms, some things that could not be cut further. But Democritus didn't get very far with his idea. The greatest Greek philosopher of the day, Aristotle, had held out for the four elements, and because of his great reputation, this false idea governed the thinking of scientists for 2,000 years, because no one dared suggest that he knew better than the great Aristotle. Bronze Age man was one of the earliest chemists. Democritus insisted that matter consists of atoms. Paracelsus told his pupils to use experiments. Boyle investigated gases and broke old traditions. In the meantime, scientists of Arabia began working in a subject they called alchemy. From Arabic al, the chemi pouring together. They mixed things and boiled and distilled and extracted in the hope someday of finding a way of making gold. They discovered a great number of things not previously known, developed many sound laboratory methods, and gave the scientists of chemistry its name. But they never created the slightest speck of gold. Neither did a great number of European alchemists. For hundreds of years, chemistry had little headway. Then, in 1525, a Swiss doctor and scientist spoke up. He had the imposing name of Theophrastus Bombastus Paracelsus von Hohenheim. He challenged his students to tear up their books with the old theories that had been developed through reasoning, only to find out for themselves through experiments whether the scientific theory was right or wrong. But only a few people paid attention to him. More than 100 years passed before an Englishman, Robert Boyle, in 1661, proceeded to and killing off the old idea of four elements. He did it by establishing that there are many elements, substances that cannot be formed by other substances and cannot be broken into other substances. Another 100 years went by. Then at the time of the American Revolution, the day finally dawned on modern chemistry. A Swede, Carl Scheelen, and an Englishman, Joseph Priestley, discovered oxygen, and a Frenchman, Antoine Laurent Lavoisier, explained the true nature of burning and made up the first scientific listings of all known elements. 28 at the time. Within a few years, more elements were found with the help of electricity. An English chemist, Humphrey Davy, in a single year brought to light 6 new metals, among them sodium, potassium, calcium, and magnesium. 20 years later, in 1828, another important breakthrough occurred. A German chemist, Friedrich Wohler, working in his laboratory, produced a chemical, urea, that had never before been made outside the body of a living animal. More and more things were happening. New elements were discovered, new chemicals created. The advance in chemistry greatly influenced industries, agriculture, and medicine. And then, in 1898, a Polish-born Marie Curie and her French husband, Pierre, discovered the miracle element, radium. This opened up a whole new age in chemistry. Within the last 50 years, chemistry has moved forward with giant steps, but not a single one of these steps would have been possible without the dedicated work of the chemists of the past, who laid the foundation of which modern chemistry rests. Priestley used heat of sun to produce oxygen. Lavoisier gave the right explanation of burning. Davy brought electricity into chemical research. Marie Curie and her husband discovered radium. Regular light pure water. Aluminum flasks. 4Ns flask. Beakers. Washable glass. Test tube holder. Evaporating dish. Wire gauze with asbestos center. Graduated cylinders. Circular togs. Utility clamp. Pinch clamp. Day. Ring support. Stand. Alcohol burner. Crucible lid. Drying tube. Filter paper. Equipment of chemistry. Some of the greatest discoveries in chemistry were made by scientists who had no special equipment, but simply used whatever was at hand. In your home lab experiments, it will pay you to follow the example of the early chemists. Put your imagination to work. Use whatever suitable equipment you can find around the house, as suggested in the column to the right, and buy only what is absolutely necessary, as shown below. Some items may be purchased in a local drugstore or scientific supply shop. If not, you can buy them from one of the suppliers listed at page 110. Later on, if you really get excited about chemistry, you may want to use your pocket money for some of the lab equipment shown on page 8. Improvised equipment for home lab. Screw top can, 1 pint. Mayonnaise jar, 4 O's. Water glass, olive jar, plastic funnel. I changed the page by accident. I'll go back. Okay, olive jar, custard cup, ink bottle, alcohol burner, wire screening, plastic funnel, homemade test tube holder, stand made of cloth, hanger wire, rubber tubing inside diameter, glass rod, test tube brush, glass tubing, 5 millimeters outside diameter, triangular rubber stoppers, number 00 to 6, test tubes, Pyrex 6mm x 150mm, wide mouth bottle, 400 OZ, red and blue litmus paper. In a regular lab, everything has its place and is near at hand. Aim to keep your own lab as well organized. Setting up your home laboratory. Box to hold home lab can be made from plywood. Keep box locked when not in use as a protection for younger children. Siphon bottle. Waste paper basket, plastic pail for waste. It is possible that you may be permitted to work at the kitchen table when this is not in use, but it is far better if you have a place where you will not be disturbed and where you can store equipment. A corner in your room or in the basement or garage. These are things you will need in your lab. Work table and sturdy table will do. Cover it with a plastic top to protect the wood. Water supply. If you have a bulkhead nearby, fine. Otherwise, make a siphon bottle. Page 11. Waste disposal. If you can dump your waste directly into the kitchen drain, not into the sink, you are alright. If not, collect it in a plastic pail to throw out when you're finished. Social feet. In regular laboratories, spherical gas burners are used. In the home lab, you can use a burner for then ethyl alcohol. Have a shallow metal pan under the burner for fire safety. Storage. If there's no one around to disturb you, chemicals and equipment an open shelf is okay. Otherwise, use a box that can be locked up. Containers. Keep chemicals in glass jars and bottles. Label them all clearly. Stands. Make your own test tube stands, as well as stands for holding glassware for heating.